Hey there, guys. I do not think I'm going to make it to class again on Wednesday. I'm still feeling pretty under the weather, and I just wanted to record this lecture for you guys so that you're not too far behind and we kind of keep moving. So, what we're going to talk about today is some of the metabolic components of muscle fatigue. We're kind of leaving the Allen paper and moving into some of the other papers. I had sent you a PDF on our announcements, which kind of covers some of this. So now we're going to just talk about the bioenergetics of skeletal muscle and how bioenergetics can lead to muscle fatigue. So we had talked about the Allen paper. You guys had done a bunch of presentations on it. And now we're going to look at some of these metabolic changes in a working muscle. And I'm sure for most of you, you're familiar with the majority of this information, but we're still going to talk about ATP. We're going to talk about the depletion of ATP, and we're going to talk about these changes in other substrates such as ADP, AMP, IMP, and PI and PCR. So there's just kind of an alphabet soup there, and in time we will talk a bit more of these in detail. So let's get into this and start talking about the metabolic components of working muscle. So as you guys are very aware, exercise demands that we have this continual supply of ATP, and it has to be maintained. And if it's not maintained, well, we know that we can't have muscle contraction at the molecular level. So when we're talking about myosin and actin, obviously if there's an absence of ATP, if there's a high level of ADP or AMP, that is going to inhibit contraction or slow contraction down. So we'll still be able to produce force, but that force production will be much lower, right? And we know that the myosin and actin binding to one another is going to be slowed down. We know that the power stroke is going to be slowed down. We know that that cycling of myosin being released and cocking back and rebinding and committing to that power stroke, that's all going to be jeopardized when levels of ATP begin to plummet. So there are three essential pathways that are associated with rebuilding ATP during exercise. And most textbooks will say three. I'm going to say four because when we start talking about glycolysis, there is an aerobic and an anaerobic component to this. And you guys are aware of that because we already have drawn these pathways in class. But the energy, the substrates that are basically being committed to rebuilding ATP, they're coming from very different places. So we have a phosphocreatine pathway, which I will draw for you guys. So it will be very clear. We have a glycolysis pathway, and that glycolysis is going to come from the glycogen breakdown. So the energy, we'll also get a little bit of energy from blood glucose, but the majority of the glycolytic pathways, which is aerobic glycolysis and anaerobic glycolysis, that's going to come from the glycogen that's already stored in the muscle. And then the final pathway is going to have fatty acid utilization. So when we start to kind of deplete this pathway and we start to deplete this pathway, well, that's going to rev up this pathway. And this pathway here is very long standing, which means we can stay in that fatty acid pathway for a very long time because we have a tremendous amount of energy stored in fatty acids. But of course, what begins to happen from here to here to here is this high intensity exercise kind of really depends on the phosphocreatine system. Moderate intensity exercise is going to depend on both the anaerobic and aerobic glycolysis pathway, and then low intensity exercise is going to going to depend on primarily fatty acid utilization. So before we move on, it's really important to differentiate the difference between these three. Now, when we talk about energy at a substrate level, and we talk about phosphorylation of ATP, which means basically putting a new phosphate back on ATP, This energy substrate level, this happens in anaerobic glycolysis or anaerobic energy systems. And this is phosphate based. And I'll show you a picture of this momentarily. When we get into oxidative phosphorylation and we get into fatty acids being used, that's not phosphate based, that's electron based. So we're dealing with two specific types of energy regenerating systems. One being phosphates, and let me just make this very clear. So let's draw a picture here, right? So one will be based on phosphates, right? And I will show you this in a very clear picture. And then oxidative, that's electrons, right? So that is passing of electrons that's going to generate the energy. So if I were to ask you what are the two major sources of energy in these three pathways, you would say, well, anything anaerobic is phosphate-based and anything aerobic is electron-based. So what does that mean? Well, that means that creatine phosphate, well, that makes sense. That's going to be phosphate, right? Muscle glycogen breakdown. So if we are in anaerobic glycolysis, that's going to generally be phosphate based with a little bit of electrons, and I'll show you that momentarily. And then when we get into aerobic glycolysis, that's going to be a little bit of phosphates and a little bit of electrons. And then when I get into fatty acids, well, that's generally just electron based, right? So this will make clear sense in a moment, right? So most importantly is the relative contribution of these metabolic pathways is primarily determined by the intensity and duration of exercise, okay? So phosphocreatine, generally high intensity. Anything with muscle glycogen, generally moderate intensity, and anything with fatty acid is low intensity. And again, we're dealing with phosphate and electrons as the primary substrates that are kind of being used to generate energy. Okay, so let's concentrate on this one first here. Let me get this up here. Let's concentrate on this one first. What is substrate level phosphorylation, right? What is that? And I told you that this happens in the anaerobic pathway. So let's take a look at this. And I want you to look at this. This should be something very familiar to you. This should be glycolysis, right? You should be familiar with this pathway. And I'm asking you, where do you see substrate level phosphorylation and where do you see electron activity? Well, if we look at the first part of glycolysis, right? So let's say we are exercising and we are in a anaerobic glycolysis. Well, then we can look at this substrate level phosphorylation, and we can see that if we have glucose coming into the muscle cell, we can see that initially we lose a little bit of energy, right? We know that there's this investment phase. So here, right, we lose a phosphate. Okay, well, that's not really generating energy, right? We're talking about where do we get energy generated at a substrate level? And glucose is a substrate, right? So that's what this is referring to. Well, when glucose moves down and gets processed, we have another ATP right here, and we have another ATP getting turned into ADP. So at a substrate level, we are losing energy right now, right? And then as we get further down into glycolysis, then what we see here is that we start to generate some ATP, and we generate 2 ATP. So this would be a phosphate generating energy at a substrate level, right? And where else do we see another one? Well, we see it down here before we get to pyruvate. We see that there are 2 ATPs being generated, which means that a phosphate is being put back onto ADP, right? So you can see the ADP right here, and a phosphate is being put back on. So if we go back and we look at this substrate level phosphorylation, right? It's happening in anaerobic glycolysis, and this is phosphate based. So we know that in this pathway, if we are using glucose, we are creating ATP anaerobically at a substrate level, right? And ultimately what's happening here, let me clean this up for you guys. If it's going to let me clean it up. There we go. Ultimately, let's clean this up one more time. We know that glycogen, and maybe you don't know this, but I'll just draw it for you guys here so you can see it. Glycogen exists here. And what do I mean by that? Well, glycogen gets stored in these polymers, right? And it has to get converted to glucose 6-phosphate and then enter glycolysis, right? And then once it enters glycolysis, it will go all the way, that glucose that's stored in the muscle, it will go all the way down to pyruvate. And we know that pyruvate is the fork in a road, right? So when we get to pyruvate, pyruvate can either go into the mitochondria and be used aerobically, or pyruvate can get converted to lactic acid and be used anaerobically, right? So we know if we go down to pyruvate, we can either move into the mitochondria or this can get converted into lactic acid. But regardless, we generated 4 ATP at a substrate level, right? And let's just go back. Let's just beat a dead horse here. I told you that these pathways, they basically work around phosphates or they work around electrons, right? So let's look at the electron story. So let me clean this up here really quick. And these should be things that you guys are aware of. And if you're not aware of this, it's okay. We could talk about it more in class. But I want you to look at this glycolysis pathway here. And I want you to tell me where electrons are being passed in the same manner as phosphates. And there should be one very clear reducing agent. And if you don't know what a reducing agent is, it's this guy right here, NADH. NADH is basically going to take electrons and it's going to take those electrons to the mitochondria where it will put those electrons through the electron transport chain. So remember, I told you that these pathways, they use one of two things. They either use phosphates, as I showed you here with muscle glycogen breakdown, or they use electrons. And if we go back here, this is one of those examples of something that is using electrons and it will get carried into the mitochondria, right? So when we look at what glucose is capable of doing, or we look at what glycogen is capable of doing, we will lose a little bit of ATP, but as we get further down into this process, we'll generate 4 ATP, and we will also generate some reducing equivalents or some reducing agents here that will carry electrons into the mitochondria and ultimately make more energy, okay? So this is just showing you the difference between phosphates being used and electrons being used, okay? And in this particular case, when we're talking about glycolysis, we're talking about the capability of using both electrons and phosphates. And we call the phosphate portion of this substrate level phosphorylation, right? And that's what's happening here. So we're using a substrate called glucose, and we're using phosphates to create energy. Okay, and this will all make more sense as we move further along. So, so here's that picture again. Now, there are some pretty significant metabolic changes that happen in a working muscle, right? I had told you that skeletal muscle stores small amounts of ATP, right? So metabolic pathways such as this have to be activated to resynthesize ATP, right? So when we go back to this pathway right here, or we go back to the slide here, we know that phosphocreatine is going to help restore ATP. We know that anaerobic and aerobic glycolysis are both going to help restore ATP, and it's going to use glycogen first, and then it will use blood glucose second. And we know that fatty acids are also going to help restore and regenerate ATP. And some of them are going to use phosphates, and some of them are going to use electrons. Okay, so that's where we are so far. So we have these pathways, right? We know that there will be energy resynthesized, but there will also be metabolites that will be produced as well. And these metabolites can be harmful to the muscle. We'll talk more about metabolites as we get a little further, right? We know that one of those metabolites are lactic acid, right? And we know that the acid portion can be harmful to the muscle, but the lactate portion is basically something that we can recycle for ATP, right? We know that lactic acid will dissociate into lactate ions and hydrogen ions, and the hydrogen ions will cause the burning in the muscle, but the lactate will be sent to the liver to basically help regenerate ATP. And that's going to happen here. So if intensity of exercise is very high, well, what happens? Well, that pyruvate will move into lactate. It will generate lactate, that's an L, that's an L, and hydrogen, right? And the hydrogen ions are what will cause the burning in the muscle, and the lactate will be shuttled to the liver to basically help regenerate ATP. So ultimately, I'm writing with my right hand right now, and I'm left-handed, so just bear with me. That says ATP. Ultimately, we have all these systems in place to regenerate ATP as quickly as we can. And the better shape that we get in, the better we get at regenerating this ATP very, very quickly. Okay, so let's kind of break this down now. Okay, let's break down the metabolic pathways. Let's break down the phosphates and the electrons, and let's talk about the differences between pardon me, anaerobic glycolysis, aerobic glycolysis, beta oxidation, and phosphocreatine pathways. All right. So if we look at this slide here, it basically tells us where most of the energy comes from, right? So I told you that we have a very small pool of ATP. I'm just going to put an S for small. We have a very small pool of ATP in our muscles ready to go, energy that is immediately available to use. And once we burn that ATP, we are going to shift to another pathway or transfer to another pathway to help what? To help resynthesize this low level of ATP that's in the muscle, right? And we know this ATP-PC system, it gives us slightly more energy than what we have in the muscles, right? So you can see that it's slightly higher, right? And I'm just introducing these pathways to you right now, just in case you're not familiar with them, right? Now, once we deplete this pathway, we want to transfer to another pathway. And that pathway is anaerobic glycolysis. Now, as you can see from the size of this bar compared to these two, this one will generate substantially more ATP. Okay, I'm writing with my right hand on the mouse. I'm left-handed, bear with me. That looks pretty good. Okay, this will help regenerate more ATP. Now, why do you have this line here, you're asking? Well, because this is the threshold of where we switch from anaerobic energy production to aerobic energy production. And if you look at the size of these bars, aerobic energy production is much more robust. We can get more ATP resynthesis and more ATP regeneration through these aerobic systems. Now, keep in mind that these aerobic systems, they do require oxygen, which means we are going to be in the mitochondria, right? So yes, glucose, because this is aerobic glycolysis, glucose can go into the mitochondria and it can generate a substantial amount of energy. And basically fatty acids can also go into the mitochondria, and this yellow is basically representing fatty acids, can also go into the mitochondria and regenerate a lot of energy, right? So this first system here, ATP-PC, this is purely a phosphate system, okay? Purely a phosphate system. Anaerobic glycolysis is mostly phosphate, but also a couple of electrons, okay? Aerobic glycolysis is phosphates and electrons, And beta oxidation, that's coming from fatty acids, right? That is primarily electrons. Oh, that's an E. Let me draw it again. E. There you go. Okay. So this energy regeneration of ATP is all due to phosphates and electrons. And depending on the substrate we use, and again, substrate is, where's the energy coming from? Let me clear this up for you so I can kind of identify that. Okay. Where is that energy coming from? Well, let me clear that for you and tell you right now where it is coming from. Okay. So when we're dealing with, give me 1 second here. ATP, we have these ATP pools in the muscle. They are already there. ATP-PC, this is coming from phosphocreatine. I will draw this for you so you understand what it is. And an enzyme called creatine kinase, right? And this is purely a phosphate system, okay? It's not coming from glucose. It's not coming from fatty acids. It's purely just reshuffling of phosphates. When we get into anaerobic glycolysis, this is dealing with glucose, okay? So glucose, because it's glycolysis, right? Sorry, I'm writing with my right hand. I operate the mouse with my right hand, but I'm left-handed. This is coming from sugar, right? Glucose, and that could be glucose that's in the muscle or glucose that's in the blood. And we know that that glucose that's in the muscle, we call that glycogen. And I hope everyone, glycogen, G-E-N, sorry about that. I hope everybody, that's an E, glycogen. I hope everybody in class does know what glycogen is. And if you don't, it's okay. I can define it for you in class. Let me see if I can make this a little cleaner for you guys. I don't think I can put any notes in there. I wish I could put in some text. Let's see. Laser pointer. Nope. I don't think I can do it. Okay. So, anaerobic glycolysis. Well, glycolysis obviously means glucose. Aerobic glycolysis, well, that means that's coming from glucose as well. So Glucose. That looks better. And that glucose could be coming from glycogen or from the blood, right? Because we have glucose circulating in the blood. And then when we get to this beta oxidation, we're dealing with fatty acids, right? So this is coming from the fat that is being shuttled out from our adipose tissue or from fat that's being stored in the skeletal muscle, right? So we have these different sort of energy pathways, and we know that there's a threshold between anaerobic and aerobic. And we know that aerobic is generally dealing with electron passing, and anaerobic is mostly phosphates, right? And this will all make more sense as we move on. So I just wanted to introduce that to you, okay? So now if we look at the next slide, I told you that in order for us to maintain ATP and energy while we're exercising, we have to transfer through these energy systems, right? So if you look at ATP, right, we have this small amount of ATP in the muscle. Once we deplete that ATP, we have to transfer to the next section, which is ATP-PC. And if you look at the size again, right, we produce a little more energy. And once that energy depletes in ATP-PC system, we have to transfer again over to anaerobic glycolysis, right? And once we deplete that pathway, we have to transfer over to aerobic glycolysis. And if we deplete that pathway or we continue to exercise for a longer duration of time, we have to transfer over to fatty acids, right? So we have phosphocreatine, we have glucose, and we have fatty acids. Now, not only do we have to be able to transfer to these higher energy yielding pathways, but we also have to be able to transfer back, right? So let's say you're doing non-continuous intermittent exercise where there's different intensities, there's rest periods, there's pausing, right? So think of like a soccer player, right? A soccer player, let's say a midfielder. They'll do a lot of sprinting, and then they'll walk, and then they'll stand still, and then they'll sprint again, and then they'll walk, and then they'll jog, right? They're never doing a continuous muscle contraction. So they have to have the ability to not only move through the pathways this way, but they also have to have the ability to move backwards into other pathways, depending on what the intensity of the exercise is, right? So if you have a midfielder that is jogging for 2 minutes, right, they'll be over here primarily. And then if they have to sprint for a ball, they'll shift back over to maybe this pathway, right? And what that is called, what we call that, let me erase all this, is metabolic flexibility. We have to have the flexibility to shift within these different pathways when the demand is necessary, okay? So far, I have given you, let me clean this up. I have given you a basic summary of these major energy pathways, right? And you can see by this very generic representation that certain pathways just produce more energy than others, right? And in order for us to continue to exercise for longer durations, we have to be able to transfer through these different pathways basically to regenerate ATP, right? So that's the goal of metabolism during exercise. So what I'm going to do now is I'm going to reintroduce again this slide and this one. This slide. This one here is a very basic representation of what I want you to know, which are the different pathways and what the pathways are doing at different time frames and at different intensities. Now, this one is a very generic representation, so let me start with this, and then I will draw my own version of this with a bit more detail. So if we look at the y-axis and the x-axis, right? The X is up here, unfortunately. Usually it's down at the bottom. Well, the Y is telling us what the total percent of energy is being used at different time frames, right? Because the time frames are going this way, and this is where the energy is coming from at those time frames. So from 0 to 60 seconds, and I don't like this 60, but it's just a general picture to show you what's going on here. Within the first few seconds, 100% of our energy is coming from the ATP-PC system, okay? So that's adenosine triphosphate, creatine phosphate. This here is primarily almost 100, well, it is 100%. I don't know why I'm telling you it's something different. This is 100% phosphate recycling, okay? And I will show you a picture in a moment of what I mean by that. Now, there's something very interesting that happens here, and I have this arrow here. You can see that once this energy system ramps up and it begins to decline, at the same time, we get this other energy system starting to rev up here, and this other energy system is glycolysis, right? So once this ATP-PC begins to fall, the sugars come to the rescue and start to increase ATP resynthesis. Now, how does the sugar know that it is needed? Well, there's something happening here that is telling the sugar that it is needed. It is telling the metabolism that they need to shift. They need to transfer from ATP-PC to glycolysis. And what is happening here is there is a shift in the ratio of ATP to ADP. ADP. So what happens is ATP starts to go down, and you can see that by this change in this slope here, and ADP will start to rise. And that is the signal. That is the signal that tells glycolysis and sugar that it needs to be mobilized to help regenerate ATP, right? So as we get into 60 to 90 seconds of exercise, you can see that glycolysis is kind of doing most of the work, right? So if we do continuous exercise from 0 to 60 seconds or 0 to 90 seconds, we are primarily using ATP-PC, and we are using glycolysis, right? Now, there's something that happens here in glycolysis as well. So as glycolysis ramps up, our ATP levels start to go up because we're regenerating ATP with glycolysis. And then once we get here, what starts to happen? Well, we get a shift in that ratio between ATP and ADP. ADP starts to rise, which means that the energy is getting very low, and ATP starts to fall. Well, once that occurs, look at what comes to the rescue here. We have oxidative pathway, which is fatty acids. We have that kind of taking over and increasing ATP resynthesis, right? So this is just a picture to show you the transfer of these energy systems. And one of the major signals that tells a new energy system to come in is the change in ATP to ADP. So that ratio, right? And this is ADP. Okay, so once ADP starts to rise, that tells these other energy systems to come into play and to transfer. So what I'm going to do here really quick is this graph here is just the same representation of this graph here, right? And I'm just kind of introducing these pathways to you, right? This is stored in the muscle. I told you guys that we have this little swimming pool of ATP in the muscle, right? Some people it's a kiddie pool, some people it's an in-ground pool, some people it's an Olympic pool. And then we have all of these pathways that will help regenerate and resynthesize this pool once we start to use all of the ATP. And we know that these two are anaerobic and these two are aerobic, and glucose is unique because glucose could be used anaerobically or it can be used aerobically. And again, just a reminder, this line here represents the shift from anaerobic to aerobic. And if you say, well, I don't know what that means, that just means that these two here are going to happen in the mitochondria. Let me draw a picture of the mitochondria. And if they require in the mitochondria, they will require oxygen, and they will also require electrons. So I'm going to write an E, okay? All right, guys, so now I'm going to try to draw this for you and try to help make sense of all of this. So this is going to be a more detailed representation of what I showed you over here. And let me just kind of familiarize you with what's going on. So you can see here, you can see here that on the on the y-axis, I'm looking at the percent of energy from different pathways. And you're like, okay, well, what is he talking about pathways? Well, you can see here I got the ATP and the PC pathway. You can see here that I have the anaerobic glycolysis pathway. You can see here that I have the aerobic glycolysis pathway. And you can see here that I have the beta oxidation fatty acid pathway. And as I mentioned before, if we go all the way back to this slide here, these pathways enable substrate level phosphorylation, right? So that's what I'm showing you here. Let me go back to this slide. I'm showing you that we have ATP being resynthesized. So what does that mean? That means that this pathway is going to take ADP and convert it. Oh, that's not what I wanted. One more time. There we go. It's going to convert it to ATP. So that's what this first pathway is going to do. This pathway here, when we're talking about anaerobic glycolysis, we're going to do the same thing. We're going to have substrate level phosphorylation. So let me take this over here, copy it, paste it. Oh, that's really big. Let me shrink it down. Let's do 10. So we're going to have that happening here. And we're also going to have some electrons being passed to this NADH, this reducing equivalent, right? And I'll show you a picture of that in a moment. When we get to aerobic glycolysis, we're going to have the same sort of thing. Because we're in the glycolysis pathway, we're going to generate some ATP. We're going to convert ADP to ATP. And then we're going to have even more electrons being passed. And then when we get to the fatty acids, we're going to have electrons being passed. We're going to create something called NADH and FADH2, and these are all going to the mitochondria. So remember, this is anaerobic, this is aerobic, and all we're doing is passing phosphates or passing electrons. That's the big takeaway here. Okay. So at the bottom here, you see time frames, right? You see 0 to 15 seconds, 15 to 40 seconds, 40 to 90 seconds, and 120 seconds and beyond. So now this is all based on intensity of exercise and muscle contraction, but just for the sake of learning these pathways, let's just keep everything nice and clean with time frames. So if I have, let me get my drawing here. Let's do this. If I have my first pathway, which is ATP, we are going to see that this ATP is going to start very high because we have a lot of it in the muscle just ready to go. Let's make it gray so that it makes sense. Give me 1 second here. Do I have a gray? I don't have a gray. We will do black for that one. It's going to start high and then it's going to drop very quickly. Okay? And that happens within the first 10 seconds. Now, after that drops, what's going to happen is the PCR system is going to recognize that there's a drop in ATP levels, and the PCR system is going to ramp up, resynthesize some ATP, and then that's going to drop. Okay? So the ATP-PC system only lasts for about 15 seconds. We only get about 15 seconds of ATP regeneration with these two pathways. All right? So let me get rid of this now so it doesn't confuse anyone. That's not what I wanted. That's not what I wanted. Yep. Keep. So let me get rid of this, and let me get rid of this, and let me get rid of this, and let me get rid of this, okay? So we can see here that the ATP-PC system, let me clean this up here, the ATP plummets very quickly, and then once the ATP plummets, we are going to get an increase in ATP-PC, and that is going to resynthesize ATP, but only for a couple of seconds, all right? So if you are a sprinter and you only operate within 15 to 20 seconds of sprinting, well, then you are a ATP-PC athlete. That means you only kind of work within this pathway here. If you are a baseball player and you hit a ball and you sprint to first base and you have to stop at first base, well, guess what? You've only used this pathway, right? You've only depleted ATP and PC. If you're a football player and you are a defensive lineman and your job is to tackle the quarterback, well, you're going to explode for about 10 to 15 seconds and you're going to deplete the ATP in the muscles and you are going to recruit the phosphocreatine system to help regenerate that ATP, right? So some athletes spend their entire career within the ATP-PC system, okay? And that's only gives us about 15 seconds worth of energy. Now, if we exceed 15 seconds and we move into these later stages, well, then we move into anaerobic glycolysis. And I told you that anaerobic glycolysis is passing phosphates, right? If we have ADP and we need to convert it to ATP, that means that we're passing a phosphate to create ATP. But this system will also pass some electrons to generate NADH, and that NADH will go to the mitochondria. So anaerobic glycolysis, that kind of looks like this. So anaerobic glycolysis is dark green. So if we exceed the ATP-PC system, well, what happens is anaerobic glycolysis, that will start to ramp up right about like this. it will regenerate ATP, and then it will start to fall if exercise continues to surpass 40 seconds, all right? So we can see this kind of trend here of depletion, transfer of the next system, depletion, transfer of the next system, right? And we know that with anaerobic glycolysis, we are using sugar, we are using glucose, okay? So let's go back a little bit. Let's go to this slide. So once we enter anaerobic glycolysis, we are using sugar, right? And I told you that that sugar is either coming from the blood or that sugar is coming from muscle glycogen, okay? Most of it will be coming from glycogen, which means it's already stored inside of the muscle. Glycogen is a polymer of glucose that is stored in the muscle as energy. And what happens is that glucose gets, that glucose will go through all these enzymatic reactions, and we will lose a little bit of ATP in the investment phase. But once we get deeper into glycolysis, you can see here that we generate an NADH. And this NADH is carrying an electron. And this NADH is going to leave the cytosol and go into the mitochondria. That's a mitochondria, where that NADH will help generate ATP in the mitochondria. But we will also generate ATP here and here before we even get to pyruvate. And once we get to pyruvate, if we're doing anaerobic glycolysis, that pyruvate will be shuttled to produce lactate and hydrogen, right? So you can see that here we've created one reducing equivalent and we've created ATP. So let's go back to my picture, which was right here. So I told you in this pathway, we will produce ATP, right? We will produce 2 ATP, and we will also produce 1 NADH, right? So if we look back, let's just beat a dead horse here, right? You can see that we produced, here's the 2 ADP, we pass some phosphates, and we create ATP. Here we have 2 ADP, we pass some phosphates, and then we have 2 ATP. Here we have 2 NAD, we pass an electron, and we get NADH. So this is showing you where the energy is being resynthesized with anaerobic glycolysis, okay? Now, I told you here that this anaerobic glycolysis pathway, this begins to rev up when ATP-PC begins to come down. And some important points to really take note of is, let me use my red, is here. Look at this intersection. You can see where the black and the green cross one another. And this is, of course, this is where that ratio of that's an ATP and ADP changes. That's where that ratio changes. That's where this starts to drop and ADP starts to go up. And that's what notifies glycolysis to begin, right? So you can see, this is where we get, that's what notifies creatine phosphate to start carrying the heavy load. And then right here, we can see a cross section again. Well, what happens here? Well, you can see that the creatine phosphate system is being exhausted, which means that ATP is dropping and ADP goes up. So then once anaerobic glycolysis takes over, you can see here, 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 and here, ATP is being resynthesized. So the ADP is being converted to ATP. And here, ATP is very high. Okay, now what's going to happen? Well, that system, if we exercise for longer than 40 seconds, that system is going to start becoming depleted. And here is where we start to get higher levels of the ADP. So now you should be saying to yourself, okay, if the ADP levels are rising, what's going to happen? Well, we have to have another shift, right? So what begins to happen is, let's get the blue, ADP levels start to rise, ATP levels start to go down, so that starts to mobilize this next pathway. And that's going to come here, and that's going to begin to drop, okay? So if we continue to exercise from 40 to 90 seconds, and there's athletes that kind of perform in that area, well, they're going to shift from ATP PC to anaerobic glycolysis and then into aerobic glycolysis, right? And we know that in aerobic glycolysis, what are we using? Well, the glycolysis is there, so we can go to this picture again. And we know that in aerobic glycolysis, we are using sugar, right? Glucose. And that sugar right here, let me just beat a dead horse. That sugar right here is coming from glycogen and is also coming from the blood, right? And remember, I told you that glycogen is usually stored here. So when glucose comes into the muscle cell, it will get converted to glucose 6-phosphate. That glucose 6-phosphate will get converted to glucose 1-phosphate, and glucose 1-phosphate will start to store this glycogen, right? And then when glycogen is mobilized, when we need that sugar during exercise, it will get converted to glucose 1-phosphate, which will then go to glucose 6-phosphate, which will then enter glycolysis. And in that process, when we're talking about what did I leave off on? Aerobic glycolysis. When we're talking about aerobic glycolysis, we are talking about, again, creating reducing equivalents and passing phosphates. So here we're passing electrons, here we're passing phosphates. So this transfer of energy really comes down to just adding phosphates to an existing ADP, or adding electrons to NAD plus, right? So the difference between anaerobic and aerobic glycolysis is once we get to pyruvate, right? In aerobic glycolysis, pyruvate is going to get converted and go into the mitochondria to start producing energy. So aerobic glycolysis will use the mitochondria. Anaerobic glycolysis will get converted into lactate, right? So this is the fork in the road. This is the metabolic fork in the road when we're exercising. Generally, if we're using sugar during exercise, high intensity exercise will produce lactate. Low intensity exercise will produce pyruvate, and pyruvate will go down into the mitochondria, and we'll get a lot of energy generated from that, right? So this is just showing us that aerobic glycolysis is using oxygen. It's using it's creating a lot of these electron carriers, and energy is being produced in a higher level because you can see the difference between anaerobic and aerobic energy production. Now, at the very end, of course, once this energy gets depleted, right, we can say right about here, we have that shift in that ratio change between ADP and ATP. Well, then we're going to get the mobilization of fatty acids. That's going to rise, and that is going to go up like this, right? And we know that the fatty acids are going to primarily use electrons to create energy. We're going to use NADH, and we're going to use FADH2 to help create energy in the mitochondria. And through the metabolism of fatty acids, we make these reducing equivalents that are carrying electrons to the electron transport chain to ultimately create ATP, okay? So before I end this lecture, and we will reinforce this when I see you guys in class, I just wanted to kind of go over this one more time. I wanted to introduce you to all of the systems, right? So we have the ATP system, right, which is basically what is in our muscle at rest. We have the ATP-PC system, which uses creatine kinase to transfer a phosphate from ADP to ATP. I will draw this in class for you on Friday. We have anaerobic glycolysis, which will use both phosphate passing and electron passing. We have aerobic glycolysis, which will use phosphate passing and electron passing. And then we have this beta oxidation fatty acid pathway, which is just going to use electron passing. And here is a generic representation of that. Let me just beat a dead horse and then I will let you guys go, right? So ATP-PC, that is going to be purely phosphate passing. Let me find, let's do blue since that is a light blue. That is going to be purely phosphate passing, and it has a time frame of about 10 to 15 seconds, right? And then we're going to get into glycolysis. In this one, it only has one glycolysis pathway, but we know that there are two. There's anaerobic and aerobic. That is going to be phosphate passing as well as electron passing. Where did that electron go? Over here. That should be a comma. Apologize. Phosphate and electron. And of course, that electron is going to have a negative, there we go, passing, which is going to help create energy, right? And that phosphate is going to be in the form of ADP to, there we go, ADP to ATP. Let me make that a little smaller. Sorry guys, I'm feeling pretty awful here. Okay, so that's going to be ADP to ATP. That's going to be the phosphate passing. And then we're also going to have the electron passing of NAD plus to, let's see if I can do it right this time. Got it. NADH. Okay, so that's the energy that's going to be created in the glycolysis pathway. And of course, the this is going to be both oxidative, anaerobic and aerobic. And then we have the beta oxidation, which is going to be fatty acids, and that is going to be primarily electron passing. And again, these reducing equivalents of NAD to NADH, this NADH is going to go into the mitochondria, into the electron transport chain to produce ATP there, right? So this system uses creatine kinase, this system uses glycolysis, and this system uses beta oxidation. So all I really wanted to do on this particular lecture is just kind of introduce these pieces to you. And if you're kind of confused about this electron passing thing, you're like, I just don't get it, right? Well, it just goes back to the glycolysis pathway, right? You guys should all have had glycolysis training by now. And essentially, you're seeing that these reducing equivalents, NADH, are being created in glycolysis. This energy is not going to be able to be used in glycolysis like this one because it has to go to the mitochondria. So it's going to take a bit of time to get there and to create energy, but the potential energy is being created in glycolysis, and then it will be used in the mitochondria. All right, so that's all I really wanted to talk about on this lecture, is showing you that phosphates are being passed from ADP to ATP, electrons are being passed, and then these are the things that's going to help regenerate that energy. And of course, my slides are a bit more complicated. My drawings are a bit more complicated because I'm giving you these times in seconds, but it's very, very important. So we will go over this in class. I will draw the creatine kinase pathway for you. We'll draw this again just to make sure everybody understands it before we move on. And I still have, as you can see here, more lecture slides to get to. So I will see you guys in class Friday. Thank you for being so patient with me while I'm getting through this. And I look forward to seeing you all. I hope you're having a great week.